You can use three-dimensional representations to help you visualize the probability of finding electrons around the nucleus. Okay, and one way you can do that is by drawing what's called an electron cloud. So here's an example of a representation of 3p orbital. You can see the way this is sketched is where the cloud is thickest, you have a high probability of finding the electron, and where the cloud is very thin, you have a low probability of finding the electron. You can also use what's called a boundary surface representation. In a boundary surface, the boundary surface actually resembles the shape of the electron cloud, okay? And it tells us regions of regions around the nucleus where the electron density is high, the probability of finding the electron is high, okay? Now, every point on that surface represents a point, every point on that surface represents the same probability, okay? And so the s orbitals have spherical shapes, so this is the 1s, and this is the 2s, okay? A spherical shape simply means that the probability of finding the electron doesn't depend on the direction you take away from the nucleus. It only depends on the distance. Now, you can have p orbitals that look like p orbitals look like this. Okay, boundary surfaces of p orbitals look like those. They're described like. Okay. Let me show you a really nice website that will help you visualize these. And you can go to this website by doing a search for, you just do a search for Davidson College Virtual Chemistry. And when you get there, okay, you click on Virtual Chemistry Experiments. And you can click on Atomic Orbitals. You're going to need a plugin for your computer called Java 3D to be able to see these visualizations. So I have it here, brought it up here. So these are three different ways of looking at visualizing a 1s orbital. So this is for n equals 1, L equals 0, m equals 0. It's a 1s orbital. You can see this is the radial distribution function we talked about earlier. You'll notice what's the most probable distance of the electron from the nucleus. 1 Bohr radius. So r here is in terms of Bohr radius. And this is the electron density plot right here in the middle. Okay, you can see, you can look at it from different axes. It's the same thing. We say that s orbitals are spherically symmetrical. You can rotate, you can have a three-dimensional, you can drag this three-dimensional plot here of the isosurface. Okay, it's a boundary surface where the probability of finding the electron is uniform throughout that surface. Typically you would interpret these boundary surfaces as a surface where within that surface you have the highest probability of finding the electron of maybe like 90–95% of the time. Okay, so that's your boundary surface for an s orbital. You can look at it from different views. Okay, so this is looking at it from the x-axis, looking at it from the y-axis, looking at it from the z-axis. So what happens if you want to look at the 2s orbital? You have 2s orbital. Here's what your function looks like. And what did we calculate was the probability of most probable distance. The average distance was like 5.56. Okay, so here's your most probable distance right here. It's further away from the nucleus, around 5 Bohr radius. You'll notice this is the electron density plot. Now this electron density plot is color-coded because when it changes color, you're looking at a wave function that's changing algebraic sign from positive to negative. Okay. Now our probability is proportional to the square of the wave function, so the algebraic sign doesn't really matter in terms of probability. So that's what it looks like. And here's a three-dimensional view. It's also spherically symmetric. Now if you have a p orbital, a pz orbital is also known as 2pz orbital, is also known as a 2p0, it's also known as 2pz. You can see This is the binary surface plot. If you look at it from the x-axis, this is what you'll see. Okay. And from the y-axis, you see the same thing. You look at it from the top, from the z-axis, that's what you'll see. And that's looking at it from the top. And you can see that your p orbital is in fact the most probable distance is a little closer to the nucleus than the 2s orbital. Okay. Now, so this is a nice website to go to explore these different functions. If you look at p orbitals, you'll find they're generally represented by 2 lobes. Okay. That's 2pz. That's 2px. You'll notice for your 2px orbital, you have a lobe on the negative x along the x-axis. For the 2py, the lobes are along the y-axis. So think of these lobes as regions of high electron density, regions where there's the highest probability of finding the electrons. Okay. 3d orbitals tend to be described by well, a 3D with m equals 0 right here. You have what's called a 3D z squared orbital. Okay, 3D 0 is also called 3D z squared. Think of it as 2 lobes and a donut on the xy plane. Okay, and then if you have 3D xz, you can see you've got lobes, 4 lobes. Okay, directed along the in between the z and x axis. Okay, you can look at it from the y axis. You can look at it from the z axis. Okay. All right. And then if you have 4s, you can see every time you go to a higher end, you get you get more of these places right here where there's a high probability of, where the probability of finding the electron is 0. These are called nodes. These are radial nodes. These are spherical surfaces where the probability of finding the electron is 0. Okay. So your function is changing sign from positive to negative, back to positive, back to negative. But look, your radial distribution function involves a plot of a square of the function, so that's why it doesn't go negative here. It just gives you bumps in the function, but they keep going back. They go back to 0 at certain distances. All right.